thank you, Roberta, and good morning, everyone. So yes, I'm working at the National Research Center of Meteorology, so at joint unit between Météo-France and CNRS. And the idea of my presentation today is to give a quite large overview of our ongoing project regarding AI for weather forecasting. So AI for weather forecasting has now become a very large topic, and basically we can say that at Météo-France we cover mainly three research topics. So the first one is a regional weather forecasting emulation. So here the idea is to replace the classical physics-based weather forecasting models by purely data-driven models. So I will describe it in detail. The second topic is statistical downscaling. Here the goal is to recover with AI fine-scale details from large-scale data. So it's a kind of also emulation of fine-scale models. I won't talk about statistical downscaling in my presentation because you will have after me the presentation of Julia, which is entirely dedicated to statistical downscaling. And the third topic is uncertainty quantification, and in the case of weather forecasting, it's about ensemble forecast. Can we use machine learning to boost our current ensemble forecast, and how can we do that? So here it's the results from an ANR project that I presented here 4 years ago. It was the very beginning with no result, and now the project is finished. So I can present what we managed to cover during the last 4 years. So let's start with the first topic, so NWP emulation. And to start with, just basic reminder about what is a weather forecast model. So I guess you all are familiar with weather forecasting models, and I will be very short here. So the idea of weather forecasting models is to predict the next state of the atmosphere. And so for that purpose, we use models which until now are mainly based on our physical understanding of the atmospheric dynamics and physics. So basically, it's made of well-known equations, in particular the Navier-Stokes equation, and it has not been questioned since the very beginning, since the 50s. But a few years ago, some persons started to think about artificial intelligence and how AI could be integrated in the process of weather forecasting. So to have a mix between physics and AI, or maybe a full AI system. So, and this thinking has led to mainly two main topics. The first one is developing hybrid systems that combine the well-known physics-based model with some machine learning parts, for instance, to speed up the computation because a weather forecast model is computationally expensive. So in this hybrid setup, for instance, you can extract some physical parameterizations that are not very accurate or very computationally expensive, and try to emulate that part with machine learning. There are other approaches, but basically the idea is still to build on the physics-based model. And the second option is much more radical in a sense. It's to fully replace the physics-based model by a machine learning one. So it opens new challenges because here you don't have physics anymore. So it raises questions about the physical consistency of the forecast you compute, and also it entirely relies on data. So it opens new questions and challenges regarding the data, the sharing of data, etc., and also the cost of the training, because AI is very fast in the inference part, but not generally in the training part. So in my presentation, I will mainly cover that topic, purely AI weather forecasting systems. So I continue with a very brief timeline to show that the pace of development of this new purely data-driven model has been much faster than the classical development of physics-based systems. So for the physics-based system, we basically started in the 50s, and here for the purely data-driven system, we basically started 5 years ago, 2020, and they have reached a level of maturity in 5 years that is almost the same as the physics-based systems. Going back in the past, so 10 years from now, I guess that no one in this room would have been familiar with machine learning. For me, a first very interesting paper is 2018 by Dubin and Bauer from ECMWF. So they looked in a very simplified framework if it is possible to emulate weather fields, for instance, geopotential at 500 hectopascal, and their conclusion was, yes, at some point it will be possible, but don't worry because we will all be retired at this time. And a few years later, so 4 or 5 years later, we had a lot of papers, a lot of studies that have demonstrated that indeed it's possible to fully replace a physics-based model by the machine learning one. And so here is a snapshot of some of these models. Maybe some of you already heard about that. It's GraphCast from Google, Pango Weather from Huawei, GenCast also from Google, etc. And after that, so the weird thing in some sense here is that the first that tried to replace weather forecasting system by machine learning, it's not National Weather Services, but it's big tech companies I mentioned already. After that, the National Weather Services tried to do the same, and the first one that managed to do that is ECMWF. So now we are in 2025, so where are we with these new machine learned models? Some interesting facts, important facts to me this year is that the first purely data-driven forecasting model has been operationalized in February, and it's by ECMWF, so Weather Center, with its AIFS model. In July, after the deterministic operationalization, there have been the operationalization of the ensemble system, the AIFS ONS. Also from DVD, German Weather Service, they made a global A-icon operationalized in September, I guess. And also another interesting fact is that the European community is very active on the topic, and there is a kind of new consortium that is growing about this topic of AI and WP, and specifically for regional forecasting at very high resolution. So here you can see all the countries that are involved in this collaboration, and it's the PI of this collaboration is ECMWF with a machine learning pilot project. So let's enter in more detail in this machine learning system. So here the thing is that the problem has not changed. We still want to predict the future state of the atmosphere. So we developed a model here that starts from the state of the atmosphere at time t and tries to predict the next step, time t plus delta t. And to provide forecast up to very long forecast range, this model is applied in an autoregressive way. So you start from initial condition, apply the machine learned model the first time up to t plus delta t, and apply again up to t plus 2 delta t, etc. And you can go at very long range if you want. From a machine learning perspective, how does it work? Basically, it often relies on 3 steps. The first one is the encoding part. So you start from physical fields, from your initial condition, for instance, and you project these fields into an abstract latent space. And then you have the processor part. The processor part, it's really the dynamical part. It's the forecasting part that will evolve your projected fields up to a future date. And then you have the decoder, and the decoder is a reverse of the encoder. It projects back from the latent space to the physical space, and then here you obtain your forecast as usual. Okay, so some characteristics. Here are some characteristics of the models that have been developed so far. So a common thing to all the models that have been proposed, so what I mentioned, GraphCast, AIFS, Pango Weather, etc., is that they are generally trained on a common data set, which is ERA 5. So I guess everyone in this room is familiar with ERA 5. So it's the best reconstruction of the past weather that we can access on a global grid at a relatively coarse resolution compared to the current state of the art. It's around 30 kilometers, but it's available since the 40s. So it's very interesting for machine learning purposes. But what is missing here is a very high resolution, because the current state of the art, for instance, at the regional scale in France, but it's the same in other countries, it's more about the kilometer scale. Also, we learn from numerical models. ERA 5, it's a reanalysis, so it makes use of numerical models. Another thing is that we could directly learn from observation, and this is one of the next steps that is coming in all these developments. So in blue here, the high resolution and learning from observations are ongoing actions at different centers. Regarding machine learning architectures, different things have been tried. So standard convolutional neural network, but also vision transformers, graph neural networks, and also neural operators I didn't mention here, or stochastic models like diffusion models that have been presented yesterday afternoon. I would say the main architectures today for the best systems are vision transformers and graph neural networks, and we are starting working with generative systems. And what is missing here is that there are no physical constraints. All these models are purely based on data, and most of the time they don't include physical constraints, mainly just some boundings to say that precipitation must be positive, for instance, but very basic things and mostly bonding. So there is maybe a room for improvement in to add physical constraints in the development of these systems. Maybe then the most important thing, how it behaves, how this model performs compared to the physics-based system. So here I extracted a figure from ECMWF publication of the AIFS system this summer. So what you can see here is, so it's anomaly correlation on the left, so the higher the better. And so IFS is in orange, red, I guess, and AIFS is in red. Yeah, the colors are not really good here, but you can identify AIFS because it seems to have a tick here in the middle. So the AIFS curve is on the top. So it's better than all the others. So AIFS has become really a state-of-the-art model. And on the right, it's a root mean square error for 2-meter temperature. So here it's a reverse, the lower the better. And you can see ECMWF IFS, so physics-based system is here. And the AIFS system is here. So it's very, very much lower RMSE than the IFS. And if you compare both, I guess it's like AIFS has 1 day advance compared to IFS in terms of quality. So it's not a thing that we obtain so easily when we update the physics-based model. Another nice property of this system is the rapid inference time. For instance, in France, to make a 2-day forecast, it takes about 1 hour, and with a machine learning model, it takes a few minutes. So it opens new perspective for operationalization, to compute faster and maybe to compute more forecasts. This is a good point, but there are also some less good points. And in particular, machine learning is a black box. It remains mainly a black box today, even if there are some tentatives to diagnose physical consistency or how the forecast and the model behaves, but it mainly remains a black box. So there is a need to develop more interpretability and explainability tools. So this is a global picture. Here I rapidly speak about AIFS because I will need AIFS later to explain the Météo-France work. So AIFS builds on the picture I presented before, so the 3 steps: encoding, processing, and decoding. And the main feature of AIFS, it's based on graph network. So graphs are very interesting because we can process data that are not gridded. So here we process gridded field, but if we want to extend and include observation in the learning process, it's very easy with a graph to include observation of any types. So it's been trained on ERA 5, and it has learned to predict 6-hour forecast steps. And then with a rollout strategy, with an autoregressive strategy, we make 6, 12, 18, etc., and we can go as far as we want. Here are some examples of what we get with AIFS. So it's a similar forecast, a precipitation forecast valid for the same date. On the left, this is a standard model, IFS, and on the right, this is a machine learned model. It's taken from the ensemble, AIFS ensemble. And so we can see different things. First, we can see that both plots look very similar to each other. And also, what we see here is that we have the same texture as in the physics-based model. Because most of the time, machine learned systems tend to smooth the forecast. But here, and I will explain that later, it's taken from the ensemble. The training strategy is not on RMSC. It's a bit different. And thanks to this new strategy, we can get a forecast that represent all the spatial scales of the IFS. Another example, so taken from ECMWF publication, is how machine learned system can represent high impact events and in particular rare events. So here they consider the case of it's not a heat wave, but it's a case of high temperature over France. So what you see here is the analysis. So let's consider it the Grand Truth. So here in the central part of France, you can see we have a high temperature. And here they compare how IFS and AIFS predict this high temperature event. It's 6 days in advance. In the middle, it's the physics system, it's IFS. And we can see that IFS strongly underestimates this case of high temperature. On the other hand, AIFS is very good in anticipating the high temperature here over central France. So it demonstrates that machine learned systems, even if they have learned on past data and mostly quite standard episodes, they are able to predict some high impact events. Well, we could also find examples where AIFS fails. Obviously, it's just an example, so don't generalize too rapidly. So let's now move to Météo-France goals on this topic of weather emulation. So we have started a very big activity to reproduce what has been done at the global scale, but for the regional scale. So typically to predict the weather over France and neighboring countries. And also, today, our state-of-the-art system is called AROM. So AROM is a kilometer scale forecast that covers France and the neighboring countries. And our goal is to emulate AROM with AI. So it requires some adaptation compared to the systems I've presented before because it's not the same resolution. So we need data adapted to this resolution. It's not the same cost also. We need to do some, oh, sorry. We need to do uncertainty quantification because at these spatial scales we need to have a probabilistic view of the thing. And we also we just started to work on explainability and physics-informed AI. So to go faster in the development of these systems, we build on the European collaboration I presented before, so the machine learning pilot project by ECMWF, and we also build upon on architecture that have been already published. I will detail that later, but here we have this one maybe is best. It's a work by the Norwegian Meteorological Institute that already tried to regionalize the AIFS. So basically, what they did, they start from AIFS, from the global system, and they refined the grid over their area of interest here. So they call it a stretch grid model because you have two different grids, the global grid at the resolution of ERA5 and the regional grid at the resolution of their own data. So here it's 2.5 kilometers. And this is a kind of thing we try to reproduce on the French area. So what data can we use? Because this is the first thing we need to think about when we want to develop such a system. So we learn from AROM data. We want to emulate the AROM system, so we start with AROM data. And what do we have quite easily is an operational archive. AROM has been running for 2008, yeah, so almost 20 years. So the system has regularly changed over this period, but we can try to identify some period with homogeneity. And so we have designed a data set that we call Titan. And it's made of 5 years of operational analysis. So analysis is the output from data assimilation. So it's the best image of the atmosphere that we can get at a precise time. So we extracted the period 2020 to 2025. This data set is quite cool because as we fine-tune the AIFS system over a regional domain, it's quite enough to do the fine-tuning. We don't start from zero. The model has already learned from ERA5. We just fine-tune, so 5 years may be enough to have a first quite good fine-tuning. And also, this data set is quite small. It's 10 terabytes, and so the training, we can train in about 2 days for our fine-tuning, so it's quite convenient. The second data set that is coming very soon is a very cool one. It's a regional reanalysis, so it's called ARA for AROM reanalysis, and basically it's the same as ERA5, but for the regional scale, and it will cover, I guess it's 50 years of data from 1960s, I guess. It's under calculation, but it's almost finished, and it will be finished at the end of the year. So in a few weeks, we'll be able to train on this reanalysis and also to compare the training with a small set of operational analysis and the training over a much larger reanalysis set. And for instance, we can tackle with a comparison of these two data sets, we can answer classical questions such as how many data do you need to train or to fine-tune a weather model at regional scale. We also have observation, but also observations are not so easy to use because they are not homogeneous. You have a different format, different grid, etc. For each observation data, so it's much more heterogeneous, also in terms of availability periods, quality, etc. So we plan to use observations, but not now. So here's our work on the high resolution emulation. So as explained before, we build on the work by these Norwegian guys. So doing a global model, but with refined grid over the area of interest. So this is not our area of interest. This is a Norwegian one. Ours is rather here. And to do that, we work within a framework that is quite new, which is called Anemoy. Anemoy has been initiated by ECMWF to develop AI and WP, and in particular their AIFS system with graph neural network, and now it has been extended to cover a wide range of applications, and in particular to cover the regional emulation. So Anemoy is an open framework. Everyone can develop, can use and can develop within Anemoy, and it's largely used by the European community. So it's our main framework now to develop the AROM AI system. So I started to explain how it works for us, but I will detail that a bit more. So the idea is that we don't start from zero, but we fine-tune the AIFS with a refined grid over France. So our training strategy is based on it's composed of 3 steps. The first one is to take the AIFS checkpoint, and the main stage for us is this one, which is called the stage C in the Norwegian paper, where we do the fine-tuning with a refined grid over France. And then we have another step, but we didn't run this step at the moment. It's a rollout stage. So here we learn to the 6-hour prediction step, and if you apply autoregressively this model, you will have an accumulation of errors. And to reduce this accumulation of error, the stage D try to optimize over several forecasting windows. So instead of optimizing only the 6-hour step, you can optimize over 12 hours or 18 hours. You do several steps of forecasting and you minimize the RMSE of all these steps, and it reduces the accumulation error. So we are currently working on the training of this stage. And what I will present in the next slide is the results of this first stage. So here are the results, very first result, because they have been obtained in the last few weeks or even days. So here what you can see is a 24-hour prediction of 2-meter temperature. On the left, this is a operational AROM forecast, and on the right, this is the AROM AI forecast. So visually, they look like very similar. If we go into details, you can find difference, of course, but they look like very similar on average. Now let's look at some scores. So here we have computed the first scores over a 1-month period, was in June 2024. On the left, this is RMSE, here the solid line, and bias, the dotted line. So in red, this is the operational AROM. In green, this is the AROM AI, and in blue, this is the AIFS. It was interesting here to add the AIFS because remember that we start from AIFS and we fine-tune AIFS to obtain our AROM AI, so we wanted to verify that the fine-tuning had a positive impact. So in terms of RMSE, it's for 2-meter temperatures, so here AROM and in green AROM AI. So you can see that we have a big decrease in the RMSE with AROM AI, and compared to AIFS, we have also a decrease. It's smaller, but it shows that the fine-tuning has worked, and we have learned something else compared to AIFS, thanks to our AROM data. In terms of bias, it's quite the same. You have quite a large bias at some lead times with AROM here in red, and with both AIFS and AROM AI, the bias is significantly reduced. On the right, this is exactly the same thing, but for 6-hour precipitation, and the results are quite the same. We have a very big decrease in the RMSE with the 2 AI models. But if we look at the bias, this time we can see that we have neutral, close to 0 bias with AROM, but we have a slightly negative bias with the AI system, which shows that we are not doing enough precipitation with the AI system, and yeah, it's a bit degraded in the AROM AI compared to the AFS. And if we look further into precipitation, so here, yeah, it's Eidke skill score, so the higher the better, and it's computed for different precipitation thresholds, so small thresholds and larger thresholds here. And if you look only at the solid line, it's the most interesting one. You can see that AROM is better everywhere. For all thresholds, AROM is better. And then you have AROM AI, and then you have AFS. So the global picture is that the AI model is good, but if we look into the details, and in particular for precipitation, but I guess we could have the same results on other variables, it still needs to be improved, which is not surprising. It's normal. We just are at the beginning of the development of this system. Yeah, so what are the next topics for the development of the AROM AI? So we'll continue the evaluation of this first prototype. We will do the training with autoregressive steps to try to reduce the errors I just presented. Then we will train on our reanalysis. We will also include more variables. Today we predict exactly the same variables as AIFS, but for operational utilization, it's not enough. For instance, at the moment, there are no wind gusts, for instance. There are no reflectivity, etc. So we'll add these variables soon. So we have a stretch grid model, and the global part has been trained on ERA 5, but we have also at Météo-France our own global system, which is called ARPEG. So we could also plan to fine-tune the global part on our ARPEG data. We will follow the algorithmic evolution. You know that machine learning is evolve at a very fast pace, and so we have to be aware of new algorithms and to include algorithmic evolutions. And we will go toward multi-source training, as I was explaining before. Today it's just training over analysis or reanalysis, but we can include observation, especially in the graph setup. It's quite easy. And also we'll start looking at ensembles. How can we generate ensembles with these new models? And also start thinking about operationalization when the results are good enough to that. So now let's move to the second part of my presentation, which is about uncertainty quantification and probabilistic forecasting. So I know you are all familiar with ensemble forecasting. So for a few years, ensemble forecasting has become a standard way of doing probabilistic forecast in the weather domain. So the basic idea is that instead of running only one forecast, you run several forecasts in parallel to take into account the different sources of uncertainty. For instance, initial condition is uncertain, so you sample initial condition uncertainty, and then you run a forecast for these different initial conditions. You can also introduce perturbation in the models or in the boundary conditions when you run on a regional domain. And in the end, you obtain an ensemble that should be representative of your forecast error, of your forecast uncertainty. And this allows you to make some probabilistic forecast. Here you have an example of probability of precipitation for a given threshold over a given domain. So at Météo-France, we have two operational ensemble systems, one for the global scale and one for the regional scale. So here I'm interested by the regional one, which is called AROM EPS, AROM Ensemble Prediction System, and in its current configuration, it's made of 25 members with a resolution which is similar to the deterministic model, 1.3 kilometers. So ensembles are cool, but they suffer from limitations which are mainly linked to constraints regarding computational resources. Running a weather forecast, it's computationally expensive, but running an ensemble, it's even more computationally expensive. And in particular, some characteristics of the ensemble are very limited by these computational resources. And one example is the size of the ensemble. If you want to have a proper representation of a probability distribution function, you need a sufficiently large number of members, several hundreds, several thousands, maybe, especially if you want to recover the tails of the distribution. But with the current resources, you don't have, you can't compute so many members. So the idea of our work is, can we use machine learning to enrich the current ensemble, so to produce members without running the NWP model. And so this was the topic of the ANR project, which was called Poesy. We are also working on that in the framework of a Destination Earth project. So the idea is explained very simply here. So we have our traditional ensemble setup, which are the blue lines. And with machine learning, we want to issue new members, which are here in violet, but without running NWP system. So we want to enrich the current sampling of the distribution. So we don't want to learn dynamics. We just want to learn how to produce new sample given some members which have been computed in the classical way. So here we have applied the method I will develop later on 3 variables, which are 2-meter temperature and the 2 components of 10-meter wind. And to do that, we have used training data from the ARM EPS. And we try to look at different research questions. So when we use machine learning, the members that we generate, are they physically consistent? Do they add some value to the physics-based ensemble? And the ultimate question, I would say, is that if we add these violet members, this machine learning member, can we emulate a very large physics-based system? Imagine you are very rich and you can compute 1,000 members with ARM. Do we have similar properties if we emulate 1,000 ensemble with machine learning? So to do that, we used generative techniques, and here I won't detail that because we have very nice introduction yesterday afternoon of diffusion model, in particular by SIBO. And in addition to diffusion model, we use also generative adversarial networks, the GAN. So the idea of the GAN is very different from the diffusion. The goal is the same. We try to emulate a distribution, but it's done in a very different way with a generator and a discriminator. So the generator tries to produce very realistic images, and the discriminator will say, yes, it's a realistic one, or no, you have been very bad. And the process is iterative until the generator is good enough to so that the discriminator cannot distinguish between real data and fake data. So here is how we have implemented this for our purpose of generating ensembles. So we have implemented 3 approaches that we will compare just after. So the first one is with the GAN. So we used the style GAN architectures for those who are familiar with that. And the idea is quite simple. We have members that have been generated by ARM, and we want to generate new ones, but in a cheaper manner. So we can start from the members we have, and we perturb these members to generate new ones. We can do that in the physical space, but if we do that in the physical space, we will break some consistency. It's very difficult to define perturbations that will preserve the spatial consistency, temporal consistency, intervariable consistency, etc. So instead of perturbing directly in the physical space, here what we do is to perturb existing members, but in the latent space of the GAN. And this is what is represented here. So the first step of our method is that we take all the ARM members, we project these members in the GAN latent space, and we perturb the member in this latent space to obtain a much larger ensemble. And then we can recover the members in the physical space by applying the generator of the GAN. So here what we have to tune two things. The first thing is how we project here from the physical space to the latent space. We use an inversion method. And the second thing we have to tune is how we define the perturbations. So we compare the GAN setup with diffusion models, and for diffusion we use two frameworks. The first one is the most common one, I would say, and it has been introduced by Thibault yesterday. It's conditional diffusion. As a condition, we use existing members, and we train with a member as a condition and with another member as a target. It's inspired by the paper by Google, which was the SEEDS method that used this training strategy. And the other method is not, I guess, very well known outside the computer vision community, I would say. It's called the SD-edit method. And the SD-edit method is closer to the method where we have implemented with GAN. So we start from our AROM member. We apply the forward pass of the diffusion, but not up to the final stage, because we want to retain this condition. We don't want to remove all the information and to get noise. So we apply the forward pass up to a certain step to retain some information, and then we apply the reverse pass to recover the initial images, but the initial images will be recovered with some perturbation. You won't obtain exactly the same image. So you will have perturbed members around the conditioning one. So here are the results where we compare. So here it's we compare only AROM and the diffusion setup. And we look at power spectra. So what is power spectra? Power spectra are the decomposition of the energy across spatial scales. And so it's for U wind, V wind, and 2 meter temperature. You have AROM in black, and you have the generated member with the diffusion in green. And we can see that we have very good consistency between the spectra of AROM and the spectra of the members generated by the diffusion. And it's a very good thing, because it shows that with the diffusion we are able to recover all the scales, to produce all the scales of a standard AROM model. Now we look here at probabilistic scores. So we are doing ensemble predictions, so there are some basic scores, and a standard score is, for instance, the skill and the spread. So the skill is the RMSE of the ensemble mean, and the spread is the standard deviation of the ensemble. And if the ensemble is properly dispersed, the skill should be equal to the spread. If the spread is under the skill, then it means that your ensemble is under dispersive. So here we compared everything, all the methods we developed. So you have AROM in black, which is the baseline, and in colors here you have the different methods we developed. So the GAN, diffusion method 1 is diffusion conditional, and diffusion method 2 is the SD-edit method. What we can see here, it's for wind as a function of forecast time here. The spread of AROM is under the skill of AROM, meaning that our AROM ensemble is under dispersive. So by adding members, we want to add also some dispersion, and that's what happened, because if you look here at the spread of the GAN and the diffusion, the spread is higher than AROM, and the skill is mostly preserved. So we have a better adequation between the spread and the skill. And among the three methods we developed, the SD-edit one is the one that adds the largest spread to the setup. So this was for wind, and here we have the same for temperature. For temperature, the picture is globally the same. So here you have arum dispersion is under the scale, which is here. So temperature ensemble is under dispersive, and with our generation method, the spread is increased, and in particular with the SD edit method in blue, the spread is increased to the same level as the scale. So here we now have a properly dispersed ensemble. Another metric is a CRPS. So the CRPS is the compares the forecast distribution to the observed distribution, and the lower the better. So you still have arum in black, and in colors our different generated ensembles. So here the conclusions are more mixed. We don't have a very large improvement of the CRPS, but here if you look at the red and the blue curve, we have some improvements at some lead times compared to arum. And my favorite result is this one. Here we compare our machine learning boosted ensemble with a very large arum ensemble. So for the purpose of this study, we generated an arum ensemble with almost 900 members. And from these 900 members, we extracted a small set of 16 members as in operation that we use as conditions to emulate new members with our machine learning approaches. And so here we compare if with machine learning, starting from a very few ensemble, we can emulate a very large ensemble computed by arum. So I will detail the results here, which are, it's not so easy to understand, but what we have represented is a difference of quantiles between the very large arum ensembles and our different trials. So here you can consider that the 0 line here corresponds to the very large arum ensemble, and so if we are able to emulate the very large ensemble, we should be around the 0 line. So let's look at what happens with the small arum ensemble. So what we daily have for operational use. You can see that for small quantiles you are above, and for large quantile you are under. And this is typical of an under-dispersed ensemble. So these are
quantiles of which quantity?
It's for wind.
Okay.
Yeah, it's for wind, and you have temperature here on the right. So with an under-dispersive ensemble, you overestimate the small quantiles and you underestimate the large quantile. This is exactly what we can see here with the blue curve. We have this kind of S picture. Now let's look at the GAN-enriched ensemble. For the GAN-enriched ensemble, we started from this 16 member and we generate a large number of other members with our technique of perturbing in the GAN latent space. It's the orange curve. And with the orange curve, you see that we are much closer to the 0 line. We strongly reduce the overestimation of the small quantiles and also strongly reduce the underestimation of the larger quantiles. And for the diffusion, the picture is the same. We have something which is much closer to the true large arum ensemble. So we go in the right direction with our method. And for 2 meter temperature, the results are also very encouraging. So looking at the small ensemble, we still have this under dispersion issue, and with the enriched machine learned ensemble, we try to reduce this under dispersion. And now, let's look at a more visual example. So you have the 2 quantiles, 2 extreme quantiles, quantile 1 and quantile 99. It's for wind forecast, and this is a small arum ensemble. This is a large arum ensemble. We see again the underestimation of the large quantile and the overestimation of the small quantile. And in the middle, it's the enriched ensemble with the GAN approach. And we can see that we fully recover the quantiles of the large arum for the large quantile, but also for the small quantile. So it's the same thing as we obtain here, but that we can that we have visually. Yeah, so it's quite a nice result. Another way of looking at that, here we have computed, so it's at a given point, I guess it's over Toulon, something like that, and it's for temperature. So you have the distribution of the ensemble members here with the color dots, and in dashed, this is the observation, and this is according to the forecast time. So here we look at the AROM EPS, and we can see that yeah, the dispersion is not very large, and at some times the observation is outside the range produced by the ensemble. And when we applied our enrichment method, we significantly enlarge the dispersion, and now the observation is within the ensemble distribution at all lead times. So this is still the beginning, because we are dealing with only 3 variables at the moment, wind and temperature, so we are far from an operational setup where we have several hundred of members. But yeah, the method is quite promising, and what we want to do is to scale to a more realistic setup. So with more variables, we also work on a small domain. We want to enlarge the domains. And our next step is to develop that in the anemoid framework. Up to now, we developed our own diffusion and GAN, and now there is a diffusion with a graph network in the anemoid framework, and we will develop that in the anemoid framework. And also we will apply this method to initial conditions. Here we apply that directly to forecast, but we can also apply the same thing to initial conditions, and then it will allow to run a machine learned forecast starting from this enriched initial condition. This is the plan in anemoid. And so this is the end of my presentation. The next slide are more questions than results. When we started this work on enriching ensembles, it was before the arrival of GraphCast, Pango Weather, etc. But now we have another way of generating very large ensembles, because GraphCast, AIFS, etc. are very cheap. We can generate very large ensemble with these new models. So, and so here we can see the different idea here. So in the previous results, the concept was just starting from the forecast here, the blue forecast, and have additional members in violet without running a forecasting model. But now we have the machine learning model, which is very cheap. We just need more initial conditions, and we can run more members starting from that. So it's another topic of research. Given the new machine learned forecasting model, how can we generate ensembles from with this model? So here it's just some ideas and questions, but there are different ways of doing that. The first one is to apply the same picture as for physics-based ensemble. You just generate a large number of initial conditions, and then you run your system. It's what is represented here. But it won't be enough, because the machine learned models also have their own errors, and how to represent the model errors in the machine learning framework is a very new question. I don't have an answer how to estimate the model error in that case. Another way of generating ensemble, and it will be more explained on my next slide, is to do ensemble training and change the RMSE, which is the standard loss for training these models, with a probabilistic loss, and in particular the CRPS loss. And the other way is to use generative deep learning. For example, GenCast is based on a diffusion setup. So at the moment, there are no comparisons of this different approach, and we don't have a clear idea of which approach is the best for generating ensemble. And so I will finish with that. How IIFS has developed their ensemble system it's based on a training on the CRPS loss. So the architecture is exactly the same as the AFS, but during training they add noise to generate ensembles. And then it's not the RMSE loss which is optimized, but it's the CRPS loss. And so the CRPS loss has also the advantage of reducing the smoothing effect of the RMSE, and it tends to produce much sharper forecast compared to the RMSE. And we are currently working on that. We have a PhD student, Adrien, who is working on that at the moment, develop a CRPS-based training for our RMAI system. So here is my conclusion. So here, machine learning for weather is a very active field of research, and it's potentially a game changer for operational application with a faster forecast with good results. So we had very nice demonstration that this model works at the global scale, but now we have to demonstrate that this model can also work at the regional high resolution scale. So this is our current focus, developing emulators at high resolution, deterministic, and also ensembles. So we are working on different flavors, as I presented. There is the RMAI, there is the enrichment of current ensemble, and there will be the downscaling also presented later by Julia. And for the next challenge, it's learning from multi-source data, including reanalysis and observation, improving on the uncertainty quantification. Also, data assimilation is the next step, and we have people working at Météo-France on emulating the analysis step with machine learning. Physics-informed machine learning and explainability are also important. And so this is the very last one, promised. Our research is, we are engaged in a number of projects, and something I didn't talk about, but it's very close to what Romain presented yesterday. It's foundation models. Up to now, we are developing a specific model for each application, a model for forecast, a model for enriching ensemble, a model for downscaling, etc. But maybe we can do all these things within a single model, which would be a foundation model, a model that learns a general representation of the atmosphere and that we can use for then specific application for weather, but also for non-weather maybe application, weather related, but non-weather forecast application. So for that we are engaged in two projects. So Weather Generator 1, which is an Horizon project led by ECMWF, and whose aim is to develop the first foundation model for the Earth system. It's based on transformer, mask token transformer training strategy. Quite similar one is a Turing project, which aims at developing foundation models, but for physical problems. And weather forecasting is an example of use cases of the foundation model, but there are also different use cases, for instance, for nuclear applications. Regarding the multi-source learning, so we have support from EUMETSAT to learn from reanalysis plus observation, and then we have more. It's a smaller project, but here that try to understand the kind of uncertainty we can recover with the diffusion model in the DRID project. So here, yeah, I will close here, and I'm open to questions if you want.